Welcome everyone in Honors Physics, and today we are going to move a little bit forward. Previously we've talked about series circuits, we've talked about parallel circuits, and today we're going to talk about what you really have. All right, we're going to talk about complex circuits. The complex circuit is simply a circuit that has a combination of the other two types. It's got some series sections, it's got some parallel sections. In fact, with the earlier equations, whenever we gave you those rules, we gave you rules for series circuits, gave you rules for parallel circuits. What I really want you to think about those as is those would be the rules for a parallel section of a circuit, for the parallel rules, and for the series rules, those would be for a series section of circuit. Now, you certainly could have an entire circuit that's series, and you certainly could have an entire circuit that's parallel, in which case those rules apply to the entire circuit. But if you have a complex circuit, then your complex circuit will obey those rules in their particular region. Now, for a complex circuit, there is no magical formula that you can put together that will solve everything in one formula. Doesn't happen, doesn't exist. Don't think you're really clever if you put one together and say, oh, look, this equation works. I have a magic formula, because it will have worked for that one problem you just did, but any other complex circuit you get, it will not function for. There is no shortcut. So what we're going to cover today is a detailed procedure and how to work with a complex circuit. Make sure you follow the complex procedure. If you don't, no shortcut in the world is going to help you with a complex circuit. The picture you see in front of you is a light fixture you might have in your bathroom, for example. And I believe there will be another video that will talk about that. We are not going to talk about that here. So you do want to take notes for this next part, and your notes are going to look a little different. There'll be some details here. So they will end up looking something like this. Notice there's a lot of diagrams here. You're going to want to draw multiple diagrams. So here's your first diagram. This is a complex circuit. It's not that complex. It only has 3 resistors in it. Notice over on the right you've got a 30 and a 60, and down the bottom left here you've got a 20, and then of course you have the 10-volt battery in the upper left-hand corner. So a question like this, we'd be looking for things like, what is the voltage across one resistor or the other resistor? What's the current through any individual resistors? So typical kind of questions. Now the thing is, when you look at this, you don't see a series circuit. You don't see a parallel circuit. You don't have 3 resistors in parallel. You don't have 3 resistors in series. Remember, if it's in series, then the current is the same everywhere in series. Well, look at the current coming out of the 10-volt battery positive end, travels along the wire, gets to the 20 ohm, goes through the 20 ohm. You got a certain amount of current there. But when that current gets to an intersection, a split, a fork, it has multiple paths. So some current's going to go this way, and some is going to go this way. They now have 2 different currents that add up to that additional current coming in. You've probably heard the phrase, following the path of least resistance. Well, the 30 ohm is smaller than the 60, so the 30 has less resistance. It doesn't mean all the current will go through the 30 ohm, but more will go through this than this. Picture this being a bigger opening. This is a smaller opening, more resistance, harder to go through. So a smaller amount goes this way, and a larger amount goes through the 30. So the 2 currents will go through their separate paths. They'll get back together at the other intersection. By the way, this intersection is called a node, N-O-D-E. And the current rejoins, goes back to the original quantity, because now that quantity comes along, back into the battery, out of the battery, and the cycle repeats. So since this wire is in series with this wire, it's the same current along this wire to either side of the battery. By the way, it doesn't matter that the resistor is here. This 20 ohm could have been up here instead, or over here. Anywhere along this singular pathway, you get the exact same results, because it's in series in that pathway. So that's why this is a complex circuit. It's got a parallel section over here. If you look at these 2, just those 2. In fact, I'm going to help you focus on those here in a moment. Pull up our magic marker here. There's our magic pen. If we circle this area here and just focus on that area, notice all by itself this does look like a parallel section of circuit. And that's what we're going to do. We're going to think about the sections of a circuit, and we'll be able to use our rules for series and parallel in small subsections of the circuitry. And we'll do our equations based on those small subsections. Okay? So that's our focus. So we're going to focus on that right-hand section to start with. We're eventually going to come up with the other numbers. The main idea is we are trying to simplify the circuit so that we can visualize it as a single battery and a single resistor. If it's a single battery and a single resistor, then it's really a really simple circuit. And we can use our basic Ohm's law to get our piece of information. So that's what we're going to do. So, since there's no single equation, we have to do it in multiple steps. So here's our first step. Our first step is to isolate that section right here. Okay? So there's your parallel section. Okay, so our first step is to simplify that section of the circuit. So we look at a 30 ohm and a 60 ohm, and in this section they're parallel. So we have our equation, 1 over resistance total. I'm doing this with the trackball, by the way, since I do not have a pen available on this. Equals our, oh, still the magic tool. That's not going to work. Let's pick a regular marker, regular pen. All right, so we have our 1 over that total resistance. That total resistance now isn't the total resistance for the entire circuit. It's the total resistance for that parallel section. So maybe RT is not a great variable. Maybe they'd be like R parallel or something like that. So the resistance in that parallel region, right, is 1 over resistor 1, which is 30 ohms. And we add to that 1 over our resistor 2, which is 60 ohms. All right, we're going to do some algebra there. And they need a common denominator. So if you double the 1 over 30, it makes it 2 over 60. 2 over 60 plus 1 over 60 is 3 over 60. So you get 1 over the resistance in the parallel section is equal to 3 over 60. Now, here's where you got to be careful. All right. So if we just plug that in the calculator and did 3 divided by 60, we'd get some small decimal. If you get an answer less than 1, you probably forgot the next step. That next step is we have to take the reciprocal of both sides of this equation. So that really means that the resistance parallel in that parallel section is equal to 60 over 3, which is 20. Okay, so 20 ohms, and that makes sense. All right, remember the resistance is always going to be smaller than the smallest resistor in parallel. So it has to be less than 30. It's probably going to be more than 1, and 20 fits the bill. Okay, great. So now I know this resistance here in this region is 20 ohms. Now we call that the equivalent resistor. So that red region, if we replace that with a single resistor, we could replace it with a 20 ohm resistor, and it would work the same as the 30 and 60 in parallel. So the equivalent resistor would be 20 ohms. I also call that the imaginary, illusionary, fictitious, not really there, but we're going to pretend it is there resistor, and we're going to draw it that way. So I'd want you to actually draw another copy of the circuit. Boom. This is the equivalent circuit. Notice I've replaced the 30 and the 60 section over here with a 20. This is our illusionary, fictitious, imaginary, not really there, but we're going to pretend it is there resistor. So now that's the equivalent of 20 ohms. Now looking at it, oh, we've simplified it. Now you hopefully see the next step. Oh, we've got a 20 ohm here and a 20 ohm here. They're in series with each other. So therefore, we could combine those two resistors. In fact, I'm even going to do that. I'm going to take a marker here, and I'm going to highlight those together like I did with the other ones in parallel, and say, hey, I'm going to replace these guys with an equivalent, imaginary, illusionary, fictitious, not really there, but we'll pretend it is there, equivalent resistor. Because they are in series, the equivalent resistance would be 40 ohms. So that means my total resistance is 40 ohms. My voltage is 10 volts. Now I can do, hey, my voltage total equals my current total. You'll bear with me. Resistance total. Okay, great. So there's my Ohm's law with the total numbers. Well, my voltage here is 10. My current's the unknown. And my resistance total is the 40 ohms. So if we do the math, 10 divided by 40, not 40 divided by 10, 10 divided by 40, we get 0.25, isn't that an adorable little 5? 0.25 amps. Remember, A is the unit, amps. I is the variable for currents. Make sure you know the difference between variable and unit. All right, so my total current is 0.25 amps. So what that means is I've got 0.25 amps coming out of this battery. And that 0.25 amps comes along and goes into this imaginary, illusionary, fictitious, not really there, pretend it is their 40 ohm resistor. But now let's go back to our previous picture, and that's why I had you draw a second copy. Didn't have you erase things and redraw them. You want multiple copies of the diagram as you change it, because now we can go back to the previous diagram and say, hey, look, remember that previous diagram? Oh, the wrong way. Go to that previous diagram. We had 0.25 amps, right? 0.25 amps was our total current. That 0.25 amps came through our resistor. Remember, V equals IR, and that means that for this resistor, it had 0.25 amps, and it had a resistance of 20 ohms. If you do 0.25 amps times 20 ohms, ta-da, you get 5 volts. That's how we use Ohm's law, and why we use Ohm's law over and over again. Because once you know the resistance and current, you can find voltage. Or if you know the voltage and the resistance, you can find current, etc., etc., etc. So now we've got that 0.25 amps, and that comes along here. Now the 0.25 amps is going to split. Some's going to go this way, some's going to go that way, and we don't know how much is going to go one, how much is going to go the other. Do not say, oh, I'm just going to use ratios and go with ratios. Because they're inverse ratios, bigger numbers get smaller numbers instead of the other way around. And if you had 3 parallel paths there, we're keeping it simple for starters. If you had 3 parallel paths there, doing ratios with 3 numbers is a beast. So no, do not use ratios. You can certainly kind of use ratios to double check your work and see if the ratios and the numbers make sense, but do not do the work with them because it's going to be too complicated for more complex circuits. All right. So we've got an unknown current in this path and an unknown current in this path. So that doesn't do us any good. But remember, we did know that this imaginary, illusionary, fictitious resistor was also 20 ohms. And it had 0.25 amps going through the imaginary, illusionary, fictitious, not really there, but we'll pretend it is the resistor. Which means the voltage around that imaginary 20 ohm resistor was, you guessed it, 5 volts. So that means in this region, it's 5 volts. Now think about this. This resistor is in series with this imaginary resistor. Remember that red block represents the imaginary resistor. So they're in series with each other. The total voltages has to add up to 0. So you have 10 volts from the battery, minus 5 here, minus 5 there, equals 0. This 5 volts and this 5 volts adds up to the initial 10 volts, which is what it should. So mathematically, it still works out. So we know this region is 5 volts from down here to up here. So now we look at our parallel rules. This is a parallel section of current. In a parallel section of current, the total voltage equals the voltage in each pathway. They don't add up. Currents add up in parallel. Voltages are the same in parallel. So if here to here is 5 volts, that means here to here is also 5 volts. Here to here is also 5 volts. It's the same voltage everywhere in parallel. So if that's 5 volts across a 30 ohm resistor, we can do V equals I R for that resistor. And if you do 5 volts equals I times 30 ohms, you get 5 over 30, which is about 1/6, which is about 0.15 something, all right, give or take. Over on this side, we have 5 volts, 60 ohms. We again do V equals IR. I'm not going to write it again. We do V equals IR. So your 5 equals I times 60. 5 divided by 60 is about 1/12, which is about plug in your calculator. I don't have a calculator in my hand. But you get about 1/12. If you take the 1/12 of an amp here, and you get the 1/6 of an amp here, add this current to this current. Remember that current came along here and split two ways. This current number and this current number will add up to 0.25 amps. They have to, because the current split over those two pathways. And the total current into that intersection has to equal the current that leaves that intersection. And when these two currents get together up here, they're going to rejoin and come back here and be 0.25 amps again. So these are double checks that let you see if your math is working out. If this current plus this current equals 0.25, you know you did your math right. All right, but this is the idea of what we do with complex circuits. We simplify, simplify, simplify. Typically starting as far away from the battery as possible, working your way toward the battery, and you're taking parallel sections, compressing them down to a single resistor. If you have multiple resistors, say we had two resistors in this pathway, we would combine them in series first before looking at the parallel section. So you're simplifying it in small little pieces. Just remember, when you get to a node, one of these intersections here, that is going to indicate when a new section starts or begins, because that's where the current's going to split. You're going to have different currents in the different pathways. But you'll have the same voltage in the different pathways. And then this region will have the same current as this region. So you are literally combining your series and parallel rules piece by piece, little tiny bit by little tiny bit. Once you know the current in this resistor and the current in that resistor and the voltage in the resistor and the voltage on that resistor, you can find power. Remember, power is I times V. So you can use your power equations to figure out the power for an object. So I don't think we talked about a power rule. We talked about the series rules, talked about the parallel rules. For power, it's actually even simpler. For power, all of these devices will use some power. How much? P equals IV. And if you did PIV for this, and PI equals IV for this, and P equals IV for that, they each have their own power, whatever those numbers turn out to be. But then if you did P equals IV for the battery, well, the battery's got 10 volts, 0.2 amps. If P equals IV, that means power equals 10 times 0.25, or 2.5 watts. That means the battery is putting out 2.5 watts of power. These resistors, when you add up their powers, you'll find out their powers will add up to exactly 2.5, because the battery is providing all the power and the resistors are using all of the power. So that's the only power rule, is whatever output power you get from your battery, all your other objects will add up to that same amount of power. All right. Meter is going to be discussed in another lecture, so I'm going to close this one out. And I'm going to see how long this lecture has been so far. There's a problem in a few pages that I'll either show you today, or you'll get those as part of tomorrow. We shall see. All right. We're going to give you some time today to practice this, because that's only about 18 minutes or so far. Remember, these are the formulas we've got to play with. You've got your series circuit rules. In a series section of a circuit, you would add up the voltages across each object, and they would add up to the total voltage for that section. The current is the same everywhere in that series section of circuit. And your resistors, to get the resistance in a series area, just add up the resistors in that area. Remember, the area stops when you hit a node, when you hit an intersection. That defines what a section is. Parallel circuit. If you get a couple of resistors broken down to just, hey, I've got 3 resistors, 4 resistors, all parallel to each other. Now, if some are in series within those parallel branches, you got to go back to your series rules, simplify those first, combine those series ones. Now you've just got individual pathways. Each individual pathway has a equivalent resistor in it. And now you've got maybe 3 or 4 resistors in parallel. They'll all have the same voltage as each other, and the total voltage for the region will be the exact same number as each branch. The currents in each branch will add up to the current that goes into the parallel section, and also equal to the current that leaves that parallel section. And then you get the special equation for resistance of resistors in parallel. 1 over total resistance of that section equals 1 over the resistance in each pathway. And again, remember, you've compressed any series resistors in that pathway down to a single resistor. So each pathway would have 1 equivalent resistor in it. And don't forget, at the very end, if you've got an answer less than 1, you probably forgot to take the reciprocal at the end. In a series circuit, total resistance is always bigger than the biggest resistor. In a parallel section, the total resistance is smaller than the smallest resistor. For any circuit, you can use Ohm's law for the total voltage, total resistance, total current, or individual components. Individual resistors have their own resistance, the current going through them, and the voltage measured across them. Power for anything is P equals IV. And if you go back further, you've got the resistance equations. Resistance of an object is the length of the object divided by the cross-sectional area of the object times that resistivity of the object. The resistivity, and thus the resistance, can be modified by this temperature equation. Remember this value with the naught here. That is the resistivity, or the resistance, at 20 degrees Celsius. Delta T is the difference in temperature above or below 20 degrees Celsius. We can combine these equations up here a little bit in the middle in that any circuit area. Remember, you've got your Ohm's law and power equations can be combined. So if you take your V equals IR and your P equals IV and you mix and match them together, this is in another lecture, I believe, you can also calculate power with I squared times R, or V squared divided by R, which means if you double the current in a resistor, you quadruple the power. If you double the voltage, you also quadruple the power. Because remember, going back to this, if you double the voltage or the current, you're also doubling the other one, because V equals IR, right? So that's why doubling either one will quadruple your power. But that means this becomes your final sheet. And if we were actually, coming back and taking tests, this would be a great start for your note card. All right. So anyway, there's your standard equations. Now here's your practice problem. Remember, relax, chant Ohm's law. Okay. So here is practice problem. Find the total resistance of this complex circuit. So by using the laws you know, figure out the total resistance. You can also figure out the current in each resistor, the voltage across each resistor. And we will have a socrative up and running for this, I suspect, and it will likely have multiple questions. The current in each resistor, total resistance for the circuit, things like that. So I'm going to stop this here, and you can go ahead and take this practice, and this will be the rest of today's lesson. All right. Good luck, and we'll talk to you later.